Hello, so we are going to continue our second lecture, which will focus on frequency principle or called spectrum bias. So we know in the traditional learning theory, if a model is very complex, then you will cause the large generalization gap. Here's an example. If we try to separate or classify two types of data points, the green data and the yellow star, and the purple star. If we use a very complex curve to classify these two types of data points, although we can easily classify the training data sets, but if we have a new data set, new data point, for example here, usually in common sense, it has high probability belongs to this purple star, but by this red curve, you will classify it into this green dot. So if you use a very complex curve to classify this data set, you will cause large generalization gap. The traditional learning theory says as the model complexity increases, the error of training samples continuously decrease, but after some point it increases. So too complex trouble. So what kind of trouble it is? From the observation of this picture, we can see, compared with these other two examples, is much oscillated. So oscillation actually is something quite uncomfortable or not good for doing fitting or classification. Now let's ask another question. If you have a model, and this model has millions of parameters, and the task is extremely simple, just need to fit 5 data points. And the question is as following: is the model going to overfit the training data? Maybe for neural network, it will say no. Yeah, let's take a look at an example. Here's a neural network with different layers, and the number of parameters is much larger than the number of training samples, which is indicated by these red data points. And we can see that for the network with different layers, it always fits these data points with relative flat curve. The question may be as following: the neural network can only express a curve that is so flat. Is it that so? No. If we put some data points here, and here, then the neural network will not only go through the original 5 data points, but also go through your new data points. That means the neural network can express oscillated curve to fit these 5 data points, but it won't. It does not want to if there is only 5 data points. So here's another example. I trained with 4 hidden layers, and each layer has 500 neurons with tinge activation function. It's very flat, a very smooth curve to interpolate these 5-star training data points. So in this one-dimensional fitting, we can see that a neural network can fit data with somehow relative flat curve. And this is a very famous puzzle in deep learning theory. It's called different names, but I call it over-parameterization puzzle here. That is, although the neural network, the number of parameters is much larger than the number of training data, it generalizes well. So here's an experiment on CIFAR 10 dataset, which in this task, the neural network is learned to classify about 60,000 color images into 10 classes. The model used here has more than 1 million parameters. So this is much larger than the number of samples, 60,000. And there are several training tricks can be used, like random crop or decay. Maybe we can ignore what exactly they are right now. the training accuracy can achieve 100%. In this experiment, if they shuffle the labels of image data, meaning for each image you randomly assign a label to the image. Similarly, for the training data, the accuracy can be 100%. And for the test accuracy, of course, it's random guess, so it's about 10%. But for the normal data, without perturbation, the test accuracy can achieve 90%, almost 90%. That means this model has very large complexity and can also achieve untrivial test accuracy. This is very different from what we know in traditional learning theory. And actually, this puzzle is proposed much earlier by Leo Bremen in 1995. After referring papers for NIPS, which is IPS now, he explicitly proposed why don't heavily. So this question, why don't heavily parameterize neural network overfit the data, is very important and very interesting. This is much important than a simple question why artificial neural network can be so powerful. Because this question has pointed out a very key factor, the number of parameters compared with the number of samples is a very central issue to start with to study the neural network. And you also have some subsequent questions about what is the effective number of parameters, or when we should stop training, and why BP can head for a good local minimum, head for a good minimum. And after these questions, he also has a comment that mathematical theory is not critical to the development of machine learning, but scientific inquiry it is. This comment, I don't think it is criticized for mathematical theory, but just try to telling a truth that the neural network is already very, very complex, and a simple math theory cannot easily handle it. What we should do, maybe we should learn from the starting from natural science. That is, we observe a lot of phenomena, then we try to understand what's behind this phenomenon. Now let's revisit what we have been talking about. Consider we are going to fit data points here. And to achieve zero loss, we have a lot of solutions. Here's an example, an oscillated one and a flat one. For an example, for a model with the number of parameters larger than the number of samples, usually you have multiple solutions. But since after training, the neural network usually can find the solutions with good generalization ability. That is the one with relatively flat curve. So these two solutions actually they have no difference in loss function. The loss function only cares about the training data. The key questions becomes what is the implicit bias of neural network during the training? Why the neural network pick up this one but not this one? Or maybe in different hyperparameter regime, the neural network may prefer this one and another one you will prefer this one. And how we can analyze the implicit bias of neural network with different hyperparameter regimes. And this is also one topic of our series lectures, which will be more carefully studied in the condensation phenomenon. So for real data, actually, it's usually too complex for study. It's almost impossible for me, at least, to study both the properties of real data and also the properties of the neural network. So we start from the learning of a very simple one-dimensional function. So here the red curve is the target function. This is x, and this is y. And the blue curve here is the output of neural network. In the initial, the neural network is completely different from the target function because we don't have any training yet. So this will be a movie, and each frame will be several training steps. Now let's take a look at how neural network recognize this target function. So after some training, you will capture the landscape, but very few points actually are consistent. After some training steps, more oscillation emerges. So for many examples, we found a neural network seems always learn from landscape to details, but not one part to another. So this is an interesting phenomenon we found during the experiments. So now let's take a look. How to study this more quantitatively. We have this vastness, oscillation, outline, details, and one concept in math to study these properties is frequency. So consider a function we can always write it in Fourier series, and this n here is the frequency, and Cn here is the coefficient, or you can say Cn actually is the Fourier transform of your signal. And for a large n, if Cn is large, meaning it has high frequency. So if Cn is not zero, means in this frequency, this function has a non-zero component. Now let's take a look if we just perform a DFT, discrete Fourier transform of your target function. And the x-axis is the frequency, and the y-axis is the Cn here, the absolute value of Cn. So you can see that this target function has a lot of frequency peaks because it has discontinuity, so it needs to have a lot of high frequency. The blue one is the DFT of neural network output at the initial stage. Now let's take a look how it learns the target function in the Fourier domain. So initially, the neural network learns the first frequency peak, okay? And after many training steps, it learns more and more high frequencies. So we can see this tendency from low frequency to high frequency. But if this experiment can really prove this frequency principle, meaning neural network learns from low to high frequency, is it this experiment rigorous? Of course, it's not, because the question is, the neural network learns from low to high frequency or learns from large to small amplitude. In this experiment, we cannot tell because these two factors are not controlled at all. So we need to perform some more simple, more controlled experiments. In this experiment, we control the amplitude of different frequency. So this target function consists of three frequency components: sin x, sin 3x, and sin 5x, and their amplitude are exactly equals to 1. And this is the output of your target function, and this rate is the Fourier transform. You have three frequency peaks. Now we want to examine the convergence of each frequency. So we define a quantity error for each frequency. This Hk is the neural network output is Fourier transform at a frequency k minus the target function at a frequency k. So this is a relative error. And this is in the training epoch, and there are three frequency peaks. Okay, so we consider three frequency: low frequency, middle frequency, and high frequency. The color indicates this relative error. So you can see there's steps here. So as the training goes on, you can see the low frequency converge immediately, but for the middle frequency, it takes more than 2,000 steps, and for the last frequency, it takes more than 10,000 steps. So in this experiment, at least for simple experiment, in this setting, we can see that low frequency converge much faster than high frequency. So this is the spatial domain of these examples. Initially, but at the very beginning, so we pick out this point. After several training steps, the output is like this. And After some more training steps, it's like a sum function, and after more training steps, it captures the target function finally. And okay, so this is a two-dimensional fitting. For two-dimensional fitting, what's the meaning of neural network learns an image? Actually, it needs to learn a two-dimensional mapping from two-dimensional coordinates x, y to grayscale. So if we inject a neural network with all different coordinates, and the neural network will output correspondingly output for each input will output a grayscale. Then we put all grayscale together by its coordinates, we can get an image. And at the first initial training steps, you can see at the first early stage, you only capture a very coarse grain. And after more training steps, you start to capture more details. And after many training steps, it captures all the details. And this is not a standard image, so we change another image. For example, a cat. We only select some pixels, the pixels with this odd position, these columns. The white column is ignored during the training, and this is the reconstructed image. At the first beginning, is very coarse grain, and after more and more training, seeing more and more details emerges. So more standard curve is this cameraman. After some training steps, you can only see where this man is, and after more and more steps, you can see even this camera. So this two-dimensional examples shows that neural network indeed learns from low to high frequency in a lot of examples. And next, we will use neural network to understand generalization by this following perspective. Next, we will use frequency principle to understand the different generalization performance in different tasks. So here is an empirical trick in training neural networks called early stopping. Usually, we don't train the neural network until the training loss achieve very small error. Here's an example here. Suppose we sample data from a function with some noise, which is denoted by red data points here. Apparently, it has some noise, so these data points are not so smooth. And now let's take a look at the loss during the training. The green data points are the training loss. We can see as the training goes on, the training loss will continuously decrease. But after some point, the test data point, test loss will increase after some point. So this training epoch should stop the training so we can achieve the best generalization error. So what happened at this training epoch? If we look at the neural network output, we can see the neural network output is very smooth and very like a sum function. And that is the most important frequency component of these training data points. So since the neural network learns from low frequency to high frequency, and the training data is contaminated by high frequency, the low frequency has significant energy, so it will not be easily affected by noise. As neural network first learns its most important frequency, the neural network can achieve the best generalization. But if the learning goes on, it will learn noisy high frequency, so the generalization will be bad. The next example is to show that the neural network cannot perform well for high frequency dominant function. First, let's take a look at two classification examples. These are our imaging classification tasks. For this first task, the neural network will receive a small patch of an image or a small image. This image has a number inside, and the neural network need to classify this image into the right category. For this task, the neural network learns a function from the pixel space to the category space. In this example, it learns from a 784 dimension input space to 10 dimension output space. And if we perform a Fourier transform of this high dimension function in one direction, we can see that this function is for training data or for the data combined with training and test data. They are all dominated by low frequency. And for high frequency, the training and test, they have some deviation. After training, we know that the neural network prefers low frequency. So after training, this blue dashed line shows that the neural network output in a Fourier space is also dominated by low frequency and consistent with the training and test data, so it can generalize well. But for another task called a parity function, this function is defined in n-dimensional space. And in each dimension, there are only two discrete points are defined. That is -1 and 1. And the output of this function is the product of the values in each dimension. This is equivalent to count the number of -1. If the number is an even number, the final output is 1, otherwise it's -1. And as we know that in the change of any dimension, the output will also change. So this function is very sensitive to input. And if we compute its Fourier transform, the analytical form is denoted by this green curve. The amplitude will increase as the frequency increases. If we only sample a portion of data, there will be an aliasing effect. So there will be some false low frequency. We can consider in this way. If several data points are not sampled, we will regard that there will be no oscillation over there. So there will be false low frequency. And we know that neural network will learn low frequency first. So it will also, the blue dashed line also show that the neural network will have some false low frequency. And since those missing parts are interpolated by low frequency, so the high frequency energy will be small than the true function. So final learned function in the Fourier space, the blue dashed line, is completely different from the true function. So in this example, the neural network will perform very badly. That is, for a high frequency dominant function, the low frequency bias function neural network may not be well performed. Now let's get back to the long-standing problems proposed by Leo Breman in 1995. Why don't heavily parameterized neural network overfit the data? Because the frequency principle is independent of network size. No matter how wide or how narrow of the neural network, it will always learn from low frequency to high frequency in our common setting. And when should one stop backpropagation and use the current parameters? In one particular scenario, for many cases, early stopping avoids fitting high frequency noise. so you can achieve better generalization. Now, why frequency principle can happen, why you can learn from low to high frequency, we will try to explore this problem by studying some factors through experiments. Now let's take a look at the activation function we often use in previous examples, that is reduce function or tinge function. This function in the spatial domain looks like this way. The reduce activation function or tinge activation function, they are continuous. And if we perform Fourier transform for these two functions in Fourier domain, we can see they have an interesting property. Their amplitude will decrease as the frequency increases. Actually, this decreasing property is very common in common functions, because if this high frequency does not decay, it will have many fluctuations. But actually, most common functions, they don't have so much oscillation. So this makes us wonder, this monotonically decreasing property related to the frequency principle. So we can design some other activation functions. Here's an example. It's called Mexican hat function. We can tune A and B here to tune the width of this function. For example, this one is much oscillated than the right one. So we can use these two activation functions to run neural networks and to see how the frequency behavior change. And we perform Fourier transform for the previous two functions. The latter one, it actually is more oscillated. So in high frequency position like frequency 10, it still has large amplitude. However, for the right function, is much smooth. The dominant frequency is at a position much smaller than 10, so this is a frequency function in the Fourier domain. And first, we use this smooth activation function for the neural network. And the target function we choose is still sin x plus sin 3x and plus sin 5x. This is the plot of the target function in the Fourier domain. It has only 3 frequency peaks. And now for each frequency peak, we examine the convergence for each frequency peak. This is the training step. And there are 3 bars, so this 0.5 is meaningless. The first frequency, second frequency, and the third frequency, we can see that the frequency colors turns red very soon. That means that training error of this frequency gets smaller very quickly. But for high frequency, the third frequency, it converges much slower. And now if we change the activation function, the Fourier transform of the Fourier function will become larger at a larger frequency. And we still look at the same target function, and these 3 bars also indicates the convergence of each frequency. And we can see there is no frequency learns faster, and each frequency learns very fast. So indeed, the property of activation function in the Fourier domain can affect the training behavior in Fourier domain very significantly. That is the first key we get, the decay of activation function in the Fourier domain. And the second experiment we study the loss function. For the first loss function is common mean squared error. For the second loss function, we add another term. Be careful, this gradient is performed with respect to input. Why we add such terms? Because in solving partial differential equations or ordinary differential equations, we often have this gradient of output function with respect to the input. And very interestingly, if we use this mean squared error, we have this low to high frequency convergence order. But if we add another term, this convergence order is not so evident. High frequency learns much faster. Why this can happen? Actually, if we perform the Fourier transform of this gradient form, is equivalent to add a c or frequency to the original Fourier transform. So it's equivalent to add more weight for high frequency. And that explains why high frequency can learn faster in this setting. So the second key is the weight of frequency in the loss function is also important. Since we have studied the two cases, one is low frequency bias, the other, the low frequency bias, is not evident. Now, we can compare what's the generalization of these two different scenarios to answer why we need frequency principle. So in the first example, that the training behavior still follows the low frequency, meaning it learns from low to high frequency. Usually in such case, the output of network in the initial stage is quite smooth. After training and the training data points, although it does not fit very perfectly, but for the test data points, it also quite good, not so bad. This is the loss of training. If we use another activation function and the frequency principle is not so evident, in such case, since the activation function is very highly fluctuate, the initial output is also fluctuate. But this is not the key. We can use some trick to eliminate this fluctuation at the initial point. And there is no frequency learns faster. For the training data, it can learn very well. But for the test data points, for this one-dimensional function, you can see in the test data points, it oscillates very much. Definitely, we often believe such oscillated function does not generalize well. So learns from low to high frequency actually is quite important to guarantee, to ensure the neural network or an algorithm can generalize well. Next, we will introduce a very simple theoretical understanding for one hidden layer and one-dimensional target function. Although this is simple, but it reveals the intrinsic reason why this frequency principle can happen. Now we consider a one hidden layer neural network with activation function tanh. This is a two-layer neural network and one-dimensional input. We will have the linear transform at the first layer, and then it goes through the activation function, and finally have this weighted summation. We can perform Fourier transform for this network form, and since Fourier transform is a linear transformation, so this summation still persists, and this AJ also stays. And since we select this tanh function, it's smooth in the Fourier domain. is exponentially decay with respect to the frequency k here. And the weight, input weight, stays in here. Now we can define the loss function at each frequency k by mean squared way. So for frequency k, this h is the network output and this f is the target function. And now by the Parseval's equivalence theorem, we can have the integration of the loss function in the Fourier domain equals to the loss function of mean square error in the spatial domain. Usually we use this spatial domain loss to perform gradient descent. Now we can just change it to the loss function in the Fourier domain. So the gradient of each parameter can be decomposed into the gradient of each loss function in each frequency, of loss function at each frequency. And we know that this exponential form, after perform anything, any gradient, this exponential form can still stay in a formula. So we can intuitively get this. Low frequency will contribute more to the gradient. Now we can reformulate this form in this way. This AK stays because we have this square term, upper gradient. This square term will leave only the exponent one term, that is the amplitude difference, HK minus FK. And this exponentially decayed term is inherited from the activation function. And all other not so elaborate terms are put in this G term. So definitely low frequency will contribute more to the final gradient. And this gradient will help low frequency converge priority, give some priority to the low frequency converge. So if some frequency, low frequency is not converging, and this Wi is small, this exponential form will dominate. So low frequency will learn first. But if this frequency already learned, this amplitude difference is close to zero, this priority will shift to the next low frequency. So the key insight is the smoothness or regularity of activation function can be converted into frequency principle through gradient-based training. And we can formulate all this intuitive understanding into a very rigorous theorem for initial training. After we have studied this frequency principle, many people realize, including us, the difficulty of high-frequency learning has already attracted a lot of attention, such as here, an important principle for the convergence of the deep learning networks and physics-informed neural networks is frequency principle. So how to accelerate the learning of high frequency is very important. And there are many algorithms has been proposed to improve high frequency learning. So I will introduce an idea which I used from the very first beginning. I started to learn deep neural network. Now let's get back to the very original idea of low frequency and high frequency. What is high frequency? Means this function is sensitive to the input. If we have a small change of the input, the high frequency means the network or the function will have a large change in the output. To make this function as a low frequency function, we can simply just stretch this function. We don't change its shape actually, we just scale this function. And now we have the same change of input, but the output change becomes much smaller. So how to achieve this scaling? The idea is also very simple. Originally, we have a function with 30 hidden neurons, I from 1 to 30. But now, we change this setting into 3 groups. And in each group, we have different scaling coefficient. For the first part, we don't have any scalings. But for the second part, we have a scaling factor of 2. And the third part, we have scaling factor of 3. We provide a lot of different scalings. And we know that gradient descent is also called steepest gradient descent, steepest descent method. Meaning we hope the gradient descent can find, for each input, can find most efficient scaling channel or scaling pathway to learn this function. But someone maybe argue that we have amplified this neural network to a large neural network, like 3 times large. But actually, we don't. We only decompose the neurons in the first hidden layer into several groups. So the size is still the same. So here's an example by solving a Laplacian equation, but we can ignore this equation for now. The exact function is a 2-dimensional function. The red and blue points indicates this function is highly oscillated, and this black region means the empty hole. So this function is quite complex, and if we use a normal neural network, it learns function like this. It smooths this function in many places. But if we use the same scale neural network, but multi-scale structure, it's easy to obtain this oscillation function. And this multi-scale idea can apply to any task, and you can have many variants. So here's another example. We can use different components to learn different frequency of the target function. Here's an example. The first one, we don't have any scaling, it's low frequency. The second one, we have a scaling, some scaling coefficient, so we can learn high frequency. And we sum the output of this 2 network as the final output, and to add a constraint to as the loss function to satisfy our constraint. And we expect the low frequency part will learn low frequency, and high frequency part will learn high frequency. In this example, we use 3 components. The first component, it doesn't have any scalings. The true function in the Fourier domain is indicated by this black curve. And the low frequency part learns is indicated by this red curve. It doesn't have any high frequency peak. And the middle scaling coefficient, we don't use the 2 component, but we add a third component. And the second component, it has a peak in the middle frequency. And for the third part, it has a peak for the third frequency. So that indicates by such decomposition, the neural network indicates the neural network in this learns each frequency component as we expected. And this is an example used to solve Maxwell equation, also use this scaling idea. And for imaging classification, this Fourier feature network, this is a typo. And the activation function for the first hidden layer can be regarded as cosine and sine. And you can see if you don't use different scaling speed here, the length is very coarse-grained. But after using this Fourier feature, you can learn very detailed structure. And we can see for this in this paper, he also changed the form of activation function to learn such oscillated target function. In this section, we will introduce a very specific model called the linear frequency principle. And this linear comes from the linear regime for neural networks. So we study the linear approximation for very wide neural network in a very particular initialization way. Here's an example. For neural network, this x is the input and this theta t is the parameter value at the training time t, and this theta 0 is the initial parameter. If during the training, the parameter does not go too far away from the initialization, we can use a first order Taylor expansion to approximate the neural network. And now we have two models, the original neural network and the other linearized model. Here's an example to show they are quite close in practical training in some sense. In the initial quite a long range of training time, the output of one neuron for a particular input for the original neural network, indicated by the solid curve, is very consistent with the output of linearized model, indicated by the dashed curve. But in the final stage, they start to deviate. But if we increase the width of neural network, this approximation will be more and more accurate. So we can perform analysis for such linear dynamics. For two-layer neural network, we can get its Fourier transform for the output function during the training. This H is the network head means Fourier transform. The C indicates frequency, T indicates training time. This is the evolution for the whole neural network output. And this is the coefficient. Why there are two terms? Because we use ReLU activation function. But we don't go into details of these two forms. And C1 and C2 only depends on the initialization. And this indicates or characterizes the difference between the target function and the network output. But there's a P here. P indicates we multiply this function by the sample probability density function. This shows if the samples, the network output and the target function are consistent at the samples, the training dynamics will stop. And this coefficient indicates low frequency learns faster, and we can perform a further analysis for this dynamics. The solution of this dynamics for long time limit is equivalent to another problem. In this optimization problem, the constraint is the network output should be equal to the label at the training data. This is consistent with the stopping criteria for this dynamics. And there could be many solutions. Which one neural network prefer? There's a minus here. So high frequency will have more penalty. That means the network will prefer low frequency. For the fourth order term, this is equivalent to minimize the second order L2 norm. It's equivalent to a cubic spline. And for the second order term, it's equivalent to linear spline. So now we can understand in this very specific example, neural network is a mix of cubic and linear spline interpolation. We can make the fourth order term much larger than the two order term. So high frequency will be penalized more. A neural network learns a quite smooth function. These black stars are training data, and the blue solid line is learned by the original two-layer neural network. And the dashed red curve is the prediction by the optimization problem. They are more and more consistent when the neural number is getting larger. So we can use L1 or L2 to measure their difference. The difference decreases as the neural number increases. This is because as the number of neurons goes to infinity, the neural network will converge to the linear regime. We can also make the two-order term large, and the high-order penalty is smaller, and we can see the result in this transition. It has a sharp transition. But the original training and the prediction are still very, very consistent. Next, we will study the frequency principle in high-dimensional real data. This is an important step to verify this frequency principle is universal in real data. And we need to differentiate the two types of frequency. It's very easy to mix. So consider an imaging classification problem. There are two possible types of frequency. The image frequency. So for the input image, for this image input, the colors are constant across different pixels. So it's a purely zero order one, low frequency. But for this one, once you change it slightly in the pixels, the colors change very significantly. So it's a high frequency one. But this is not a frequency used in our imaging classification problem. So what's the meaning of the frequency in the classification problem? So here's an example. In the adversarial example is a very good example. So consider a picture, and now you only slightly change it in some direction, very slightly change. The image frequency actually almost does not change, but the output now is a significant change from panda to gibbon. So although the input image frequency does not change, but we know that there is high frequency very close to this point in some specific direction. And this frequency is called response frequency or a general input-output frequency. So here's an example. Consider an input of 784 dimension. Now we slightly change the input, and the output has significant change. So we call that across the around this point in some specific direction there is high frequency. But to verify frequency principle in high dimension actually will suffer from curse of dimensionality. So consider we have a problem in d-dimensional space. We can use non-uniform discrete Fourier transform. So this is the data pair, input and output, and we can get a Fourier transform. The Fourier space has the same dimension as the original spatial domain, so we can reconstruct the signal from the Fourier domain. Even when we only evaluate each dimension by 2 points, the total number for the whole space will be 2 to d points. This is exponentially increased with a dimension. So it's almost impossible to characterize this function exactly in high dimension. So we have two approaches. One is called projection. We choose a very specific direction in the Fourier space to see this Fourier transform, this frequency distribution. And the second one is called filtering. It's a coarse-grained way. So for the first one, we choose the frequency at some specific direction P1 and only change the frequency K here. And we plug in this one into the original non-uniform Fourier transform. So this P1 can be combined with X. And we define this Vi as the I's example projected into P1 direction. So this is equivalent to one-dimensional Fourier transform. We can select the direction where data has the largest variance. That is the first principal direction. Now let's take a look. Here for the MNIST dataset, this is the Fourier transform in a particular direction. And we select some frequency peaks to avoid some aliasing effect and so on. For these peaks, there are 4 peaks, 1, 2, 3, 4. And this is the training epochs. And the color indicates the relative error. So the low frequency, the color turns red very quickly, means low frequency converge very fast, but the high frequency converge very slow. For the second approach, we call the filtering. So in the Fourier space, we can regard it all the frequency with amplitude smaller than K0 as a low frequency, right? And others as a high frequency. So to keep this function only at low frequency, we only need to product this Fourier transform with an indicative function in the Fourier space. So this indicative function equals to 1 when the amplitude of frequency is smaller than K0. This norm of frequency is smaller than K0. But we actually want to do this in the Fourier domain because it's tedious and suffer from high dimensional curves. So we can use Gaussian to approximate this indicative function. The interesting thing is that Fourier transform of Gaussian is still Gaussian. And the product in the Fourier domain is equivalent to the convolution in the spatial domain. So the low frequency can be regarded as the convolution of the label with a Gaussian kernel. And we can get low frequency. And by the difference of the original one and the low frequency one, we can get high frequency. And we can do this for network and also target function. Then we can compute the relative error for the learning and also high frequency relative error. Now let's take a look. For different data set and different network structure, low frequency relative error always converge earlier for different Gaussian kernel. So this indicates the neural network learns high frequency low slower for high dimensional data. And finally, we will have more experiments for non-gradient descent training. So for conjugate gradient algorithms, so here we only change the optimization method. The target function is similar and the network is also similar. We also evaluate the relative error for each frequency peak. And we can see low frequency converge much faster. The only difference still is only the optimization method. For MNIST dataset, for fully connected or convolution, low frequency always converge. Similarly, for truncated Newton algorithm, low frequency also converge faster. Or BFGS and different settings and different dimension experiments. And for non-gradient method, like Paul Weir's method, it doesn't use any gradient information, or PSO is a particle method. Low frequency always converge. And even for this multicolor like algorithm, that is, for each parameter, we choose another in next step. We randomly choose one and its neighbor. Once the loss of this new one is smaller, has smaller loss than the current one, we choose this one as the next step. So this is a particularly very simple, very naive way without any gradient information. And we can see that low frequency still converge much faster. So let's have a final summary that we introduce a very common frequency principle, or called spectrum bias, that network learns from low to high frequency. And our experiments will also start from one dimension to high dimension. The theory can also have one dimension to more general, but we don't talk too much about general case. And it also indicates neural network is good for low frequency function, but bad for high frequency. To accelerate the learning of high frequency, we propose this multi-scale deep neural network. And actually, there are quite many ideas, very similar. And we also show some experiments beyond gradient-based learning.